Welcome to Lesson 13b, Single Drop Collection Efficiency. Last time we laid the groundwork for single drop collection efficiency. Today I'm going to introduce the Calvert and Englund model for single drop collection efficiency. So quick review, last time we got this expression for the single drop collection efficiency, that D stands for drop, and it's a grade efficiency because it's a function of particle diameter. So quickly reviewing, what this R1 means is that any particle that's within that R1, if you're here, it will travel up and hit the drop from the point of view of the drop standing still. We're moving with the drop. Any particle outside of R1 will not hit the drop, but will veer off, will not be collected. So this is a capture area. I have it in red at the bottom here. Capture area divided by the projected area is basically what this is. And so what's left is to find an expression for R1. How do we do that? Well, let's first list what R1 is a function of. In general, this will be a function of the particle properties. So we have a dp and a rho p. The collector, which is the raindrop, has similar properties, dc and rho c. And then, of course, we have the air, rho and mu. Just a word of caution here, there's three rhos. Rho of the air is rho of the collector or the drop is rho c, and then rho of the particle. So make sure you don't confuse these rhos. There's also two different diameters, dp and dc. So before we get into any equations, dc, rho c, rho, and mu, we can use these to calculate VTC, the settling speed of the drop or the collector. Similarly, we use dp, rho p, and then rho and mu of the air to calculate VTP, settling speed of the particle. Now you know how to do this, and hopefully if you've been listening to what I've been saying, you already have software to do this, so it's just a matter of plugging in. You're going to have to do this twice, once to get VTC and once to get VTP, remembering that you're going to have different densities, different diameters, but they're in the same air, so these guys are the only thing that stays the same. Plug all these into your software at a given pressure and temperature so that you can calculate rho and mu and lambda and Cunningham and all that stuff. There'll be a different Cunningham for the two different size particles. There'll be a different Knudsen number, different VT, and you'll have to iterate. So how do we find this R1? Well, you can do a CFD analysis of the air streamline going around this drop. This is DC. And then you can use your CFD analysis to predict where that particle is going to go. And the one that just kind of barely hits the drop for a given diameter, that is defined as our R1, where we're plotting the particle trajectory here. How to find R1? You can use computational fluid dynamics, CFD, or you can do experiments and then generate empirical curve fits. And several people have done this. We're going to look at the experiments. We're just going to pick one of them, in fact. I'm going to use something called the Calvert and Englund model. Notice this is a U, not an A. It's not England, the country. His name was Englund. I'll call this the C and E model for brevity. This is the only model we will use in this course. It is an empirical model, and here's how it works. First, you define capital K sub P, which they call an impaction parameter. Kp is equal to Cunningham correction factor, rho p minus rho, dp squared, VTC minus VTP, absolute value, divided by 9 mu, and then dc, the collector drop diameter. Let me just list what each of these variables are to make sure you're not calculating this incorrectly. C is the Cunningham correction factor for the particles, not for the drop. Make sure you use the correct one. You're going to have two different Cunningham correction factors. Of course, dp is the particle diameter, rho p is the particle density, dc is the collector diameter. Remember, the collector is the drop. VTC is the settling speed of the collector, the drop, and then VTP is the settling speed of the particle. For review, we're always talking about one particular particle diameter at a time. So that VTP is the settling speed of that particular particle diameter and particular particle density. Once we have everything set up, we can repeat for a range of particle diameters and get a grade efficiency. So once we have the impaction parameter, then Calvert and Englund came up with an expression for R1, namely this Kp divided by Kp plus 0.7. I'll call that equation 2. And then from the previous lesson, we know that A to D of dp, the grade efficiency, that's a single drop collection efficiency, is R1 over RC squared. So this becomes Kp over Kp plus 0.7 squared. So that is the C&E model for single drop collection efficiency. Some comments. Number one, the collector chases the particle. Generally, it's falling faster than the particle. So we have our VTC, and then we have some particle below it, and it's moving at VTP. So it's the relative difference between these two that's important, and that's why we have a VTC minus a VTP up here, the relative speed between them.
I like this word, relative.
Thanks, Albert. I think we already know that. But notice its absolute value, because what can happen is, especially if you have some very heavy particles, what happens is sometimes if the particle is big enough or if it's heavy enough, it can actually have a VTP that's greater than VTC, and then the particle would be impinging from the top onto the drop. It'll still get collected that way, so you still have a collection efficiency. But when VTC minus VTP is 0, they're both falling at the same speed, and therefore they never hit each other. So relative speed is important. And number 2, as I just said, when VTP equal VTC, no impaction is possible because they're both falling at the same speed and they can never hit each other. Therefore, Kp is 0 from equation 1. You can see that Kp is going to be 0. And then that makes A to D as a function of dP 0. And that makes sense physically. Number 3, as dP approaches dC, the model begins to break down. For example, imagine a drop of that size hitting a particle of this size. When it hits, it would probably just break the drop apart into little pieces and destroy your drop. Here's a rule of thumb. This is really my rule of thumb. I didn't find this in any textbook, but I don't trust the C&E model unless 2dP is less than dC. In other words, I'll give them a factor of 2. If the particle's more than half the size of the collector, the C&E model doesn't really work anymore. Let's do an example. We're given raindrops of diameter 200 microns and unit density. Rho of the collector is typically the same as that of water. These are water drops, so we'll call that 1,000 kilogram per meter cubed. Are falling through density air at SATP. If I gave you different temperatures and pressures, you'd have to calculate these quantities. Aerosol particles of particle density, different, 3560, and diameter, we picked 5 microns as an example here. Calculate the single drop collection grade efficiency, A to D dP, as a percentage to 3 significant digits for these particles. So first, I calculated VTC for the raindrops due to gravimetric settling. I iterated the way we've done many times. You should get 0.729937. I repeated for the particles, iterate again, and I get 0.0027100 meters per second with a Cunningham correction factor that I'll also need. Now I complete the problem by using the Calvert and Englund model for the raindrop collection. First, I calculate Kp, Cunningham for the particle. Difference between particle density and air density. I've seen students make mistakes where they put in the raindrop density there 1,000 instead. That's not correct. This rho is rho of the air when it has no subscript. Particle diameter squared, watch your units, absolute value of the collector terminal settling speed minus that of the particle. Those are in meters per second. And then 9 viscosity, and finally dC. And you could verify that all these units cancel so that Kp becomes non-dimensional. I think I forgot to mention that before, but this Kp, it's a non-dimensional parameter like a Reynolds number. I get Kp equal almost exactly 2.00958. Keeping lots of digits to avoid round off error. Now I use my equation for A to D at this particular dP, which is 5 microns. Just plug in that Kp, so that's a nice easy equation. And I get 0.55006, or since I asked for percentage, multiply by 100, and I get 55.0% to 3 significant digits. Now, since A to D is a grade efficiency, we can repeat for a range of dP. I redid this with dP equals 0.1 to 100 microns. Keeping in mind my rule of thumb, these drops are 200 microns in diameter, so I'm only going up to 100 microns, half of that as my maximum. I really don't trust Calvert and Englund model beyond that, and 100 microns is probably pushing it anyway. I used Excel, and then I have the plot on the next page. I actually did 3 different collector particle sizes. These are the drop diameters in microns. So the 200 is the one that we did as our example. That's the blue curve. And just for a sanity check, here's my 5, and I go up to about 55, which agrees with my calculations. But I also did it for 100 and for 300 microns as the collector diameters. So they look like a typical S curve, except at 200, you see it's starting to drop off here. And the 100 micron drop case has this really funny thing going on. What's happening there? Well, for any of these drop sizes, there's going to be some particle that just happens to have the same settling speed as the drop. And so if you think about it, as I mentioned, when these two settling speeds are equal, Kp goes to 0 and A to D goes to 0. And it's actually quite steep around that diameter. For this particular case, for 100 micron drops, it turns out that around 50 microns, those two particle and drop speeds are the same, and it suddenly drops to zero. I didn't have enough resolution to go exactly to zero in my range of particles. The other thing you notice is that as DC goes up, we get better performance. Our DP cut moves to the left at 50%. In other words, we're doing better with the bigger raindrops. The difference between 100 and 200 is pretty good. The difference between 200 and 300 is hardly noticeable. So we've reached some kind of diminishing returns here. It's better to have bigger particles, but only to a certain point, then it's no longer doing you any good. So just a little comment why we might expect the raindrops to perform a little better when it's bigger. Well, using our sketch that I've shown several times already, from a frame of reference moving with the drop, there's our air streamlines, and particles in the middle hit the drop. Particles on this particular streamline may just barely hit that drop. We'll call this R1. And as these particles veer along this curve, there's a radius of curvature of that air streamline. And recall, the radial acceleration towards the outside of the air streamline is u theta squared over Rm. So let's think about this. As DC increases, VTC increases. U theta is directly proportional to VTC because the faster the collector falls, the faster we fall with it, and that's directly proportional to U theta. So U theta goes up, but RM also goes up as DC goes up. Imagine I just take this figure I have here and zoom so that it looks bigger and make the particle bigger. I still have the same streamlines relative to the drop, so RM gets proportionally bigger. It turns out that these two effects are kind of fighting each other. The numerator tends to make the acceleration go up as DC goes up. The denominator tends to make the acceleration go down as DC goes up, but the numerator is squared and it wins in a sense. So in general, inertial separation acceleration goes up as DC goes up. And that's why we see a better performance as DC goes up. The curve actually shifts to the left, not up, because it goes up to close to 100%. But there's diminishing returns because even though the acceleration is higher, you also have a bigger and bigger distance for the particle to travel before it can get caught by the collector. So it turns out that at really big drop diameters, you don't gain much, as we see on this diagram. So finally, as I always say, make sure you can get my numbers here for this example, and you should be able to do well on the quizzes and homeworks.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.